we've already looked at the bonds. We know that several types of bonds can have polarity. Basically, if there's a difference in the atoms, and they aren't the same atom, and the polarity difference is more than 0.4, you're going to be getting a polar bond. And that's the majority of bonds. If you have the same atom, then you aren't going to have a difference. And there's a few atoms, or if you put them next to each other, there isn't a huge difference either. But in general, that's what you're looking for, is just a significant difference between the central atom and atoms attached. Now, that's for the bond. Overall, there can be an effect too. So if we go back to that boat idea of electrons and they're being shared evenly, this is our bond right here. And if our electrons are both just sitting right there, if they're just averaging nicely in the middle right here, making like a negative middle, like both the electrons are in that negative space there, and then both the electrons are in that negative space there, they're evenly spread out across the molecule, then that would be something that overall is nonpolar. Now, another situation could be where these electrons are in this direction and then these electrons are in this direction. Now, if you think about the boat, now we have one side of the atom that's kind of tilty, and it could tilt like, downwards and like be attracted to other things. And it's not really like these atoms tilt downwards, but they do have this attraction where suddenly they start becoming attracted to other things. So this situation would look like an example of something that could be polar. So I'll put over here, oops. Let's see if we can get it to copy the picture. There we go. So that might be something that looks polar. But if those negative charges are in the middle, it'd be not polar. Here's the case that will throw people sometimes. You can also say, well, that negative charge isn't there. It's actually way over. I'm trying to move it. It's way over here. They're like, okay, well, look, I'm polar that way and I'm polar that way. Well, if you think about the boat again, if you have a person on either side of the boat's fine, it's balanced. The problem is if you have too much negative charge, like in one direction or the other. So this would be nonpolar, the way I've drawn this. So if we have an equal arrow going this way and it's equal going this way, like those are the same elements on the outside and the middle's beryllium, if they're equal, then it's fine and they don't cause polarity. Now you have to start thinking when you think more in the 3D kind of an idea, because remember again, these are atoms, and I'm just going to put like a hydrogen there. Oops, that didn't look like hydrogen. I'm just going to put like a hydrogen here and a hydrogen here and a hydrogen here, something like that. So again, if our bond you can't put a hydrogen in the middle, but if the bonds were evenly spaced, the electrons, where they were just evenly sitting in the middle there, so their negative charges were all even in the middle, well, then it would be fine. It would be nonpolar. But we're trying to see if something becomes polar. So one situation of everything becoming polar could be if this set of electrons right here moves in towards the center. Try and get it to move. And then these electrons over here, some reason, if they were moved kind of outwards. So I'm trying to do a picture for everyone where you can get a sense for the electrons and what they might look like. I'm trying to get that pair to go up, but I'm going to erase it. There we go. So you'll see here, like in our boat, again, we have like an electron kind of near the middle, and then we kind of had two electrons more on the side of the boat. That would be unbalanced. But if this pair was out on the edge, now our boat is balanced again because it's all evenly spread out all around that atom. So let's kind of look for these first two examples over here. So we're going to go and find something that's nonpolar, so it's linear. Some of these linear pictures right here. So this HH bond, these are the same elements. So there's no way that bond is polar. If you don't have a polar bond, then the molecule's not polar either. But let's look at the BeCl. And do you see how we have these arrows drawn? So what those arrows are saying is that there's negative charge on this side of the bond and on this side of the bond. The electrons are hanging out near their arrow side of the bond, and they're not very much in that middle section of the bond. So those bonds, yeah, they're polar, but look at the overall picture. Do you see how like there's a negative on either side, like that across the molecule? Those two directions are canceling each other out. It's like the sides of a boat, like they're going to be balanced. That boat will be balanced and it'll be fine. So that's not polar. And then over here, the negative part, it's sitting more on by the edges of the arrows. And again, like if you imagine like a flat, say these are all sitting on the deck of a boat, they're all evenly balanced, so it's not going to tip. This one too. Now this one's a little trickier to see. You have to imagine it as the bottom of it is a pyramid. So here's our pyramid over here on this side. So see the pyramid and then going upwards. And so you kind of have to imagine like as long as there's something negative on all of the edges, then you're okay. And if that negative is the same something. So these are all bromine, so they're all the same polarity. So they're okay also, and overall the molecule does not have polarity. Now, here's where it comes into play. Most of the time when you have all the same elements and no lone pairs, I mean, you're not going to be polar if you have all the same elements and no lone pairs. So those examples I just showed, they were all the same element, no lone pairs. Lone pairs definitely will affect things. So now we've got a boat. So let's say our boat is a triangle, a flat triangle. That's the surface of our boat, like we're looking down at the boat. And what this is saying, if we go ahead and we do our bonds, so they are going out towards the chlorine. So there's like a negative here and a negative here and a negative here. So that would be balanced, except that we have a full pair of lone pairs also over here. So now you can see it's unbalanced again. So this would be an example of something that's polar. And then let's look at like our oxygen. That's kind of a triangle shape in a little bit of a way too. I'm going to maybe make it, I'm going to put a negative charge there and a negative charge, sorry. It's going in this direction, and it's going in this direction. So the negative charge is going to be right near the oxygen, and there's negative charge on the top. So I'm just going to say, like, in a square surface, in the middle, we've got some negative charges, and then also on the top, we have negative charges. So you can see that that's also polar. Now, if the idea of a boat like sinking doesn't really resonate well with you, you can also think of this as like a bungee cord. I've done this before, where like if you imagine that when the atoms are the same on both sides, and then you imagine like pulling it on both sides with a bungee cord, does the bee move? So if it's the same bungee cord because they're the same elements and it's getting pulled away from the boron, as long as it's happening equally, that boron won't move. That would be nonpolar. Or again, like if you have a central atom here and it's being pulled with bungee cords from 3 points and they're all the same, exactly the same bungee cords, again, if the boron doesn't move, then you are nonpolar. But if you have an extra strong bungee cord here and you pull just as far, then it'll pull your boron in that direction, and that would make it polar. So polar has to do with the charge balance across the atom, and it has to do with the electrons where they want to sit, and wherever they're sitting, they create just a tiny bit of negativity, just the tiniest bit. But it's a strong effect across the molecule. So look at these other atoms. I kind of gave a hint when I said, hey, when you're have all the same elements on the outside, then you are probably nonpolar. So use that as an idea and go ahead and try these next 6 elements and see if you get them correct for their polarity.